Hey there! So this is part 4 of the Bouncing Particles in Ideal Gases set of videos where we're trying to build up to this idea that the pressure of an ideal gas is equal to its density times VRMS squared divided by 3. So in the last part, we determined that if we had a box of n particles and we restricted the motion of the particles to only move in the x direction, we could find the pressure on the walls of the box to be rho times the mean square of the velocities, right? Which again, we're only restricted to be in the x direction, right? So of course the next step would be to get rid of that restriction that the particles can only move in the x direction and allow them to move freely in the x, y, and z directions, right? So I have a 3D picture, and each of these particles can now move around. So the first thing that we're going to do to tackle this next problem is let's go ahead and just pick one of these particles that we're looking at. How about I'll use this guy right here. So this is some ith particle. I don't know exactly which one it is. We'll just call it I. And it looks like this guy has a speed, or a velocity, excuse me, that points like this. And let's go ahead and call this guy V. Right? And this guy's going to break down into now 3 components, right? So we can break this down like this. There's my kind of diagonal, and then something like this. So we have 3 components basically. Something like this. So if this is my x, y, and z direction, then we would have a vx component, a vy component, and a vz component, right? And of course we know that just based on Pythagoras that v squared would be equal to vx squared plus vy squared plus vz squared. And actually, let's be very specific. Since this is the ith particle, I'll go ahead and add in that this is, there we go, change colors, there we go. That this is vi, this is v xi, vyi, and vzi. So we'll go ahead and just edit this just a little bit. There we go. Right, so this is just Pythagoras. We're able to relate the magnitude of this velocity vector with its component bits. Okay, awesome. So now that we're here, it's very intuitive then that for averages for lots of particles, so let's go to for lots of particles, instead of just looking at, a single speed, we could relate the averages. So my average, my mean square, the mean square of my velocities would be equal to the mean square of my x velocities plus the mean square of my y velocities plus the mean square of my z velocities, right? And if this seems like a big jump, we can do this a little bit more explicitly, and we can recognize we could divide this entire equation by n, and we could sum this up over n particles, right? So we could go sum from I equals 1 to n vi squared over n equals the sum from I equals 1 to n of vxi squared over n plus, and now we're just getting a little bit overly explicit, I'd say, but that's okay. Oh, whoops, this should be a Z. There we go. Right, so all we've done there is just recognized that once we have this for one particle, we can sum these ideas up, right? And then just divide by the number of particles, and the left and right sides of our equations will still be equal. And then we just take these guys and we notate them as such. Okay. So the next key point to talk about when we're discussing lots of particles would be that, the directions of these velocities are effectively random, right? And same with the sides of the velocities. They're just bouncing into each other. This is super chaotic, and so the velocities just kind of get distributed out randomly. So this Vxi, this Vyi, and this Vzi, for just some particle, the ith particle, I don't really know what those guys are going to be. They're going to be randomly distributed. That's all that I know. But what that means is, if they're randomly distributed, that means when I go through and I average all of these guys up, that they're going to be equal, right? So I can conclude that the mean squares of each of these components, the x, y, and z components of my velocities, are all going to be equal. This is just purely a result of for having a lot of particles that, the velocity in each direction is going to be randomly distributed. And so we can make this conclusion here, that their mean squares are all going to be equal to each other. So with this, we can really rewrite this equation up here as just 3 times the mean square of the x velocities, because these 3 guys are equal to each other. And with this, we can write my mean square of my x velocity, or my x speed, just like that. And now all we have to do is substitute this guy in to our equation that we got in the last video. And so we determine that the pressure would be equal to my gas's density times the mean square of the overall speeds divided by 3. And of course, don't forget that this mean square speed is really the same thing as just taking our root mean square speed and squaring it. And so we can rewrite this pressure as rho times VRMS squared over 3. And with that, we've really concluded what I wanted to get to by the end of this little set of videos. I guess the only thing that I'll do in the next one to kind of wrap things up nice and neatly is talk a little bit about degrees of freedom and then relate this to the ideal gas law, because I think that will make a neat end to this little set of videos. So with that, I really hope you enjoyed this process. Thank you so much for watching.